Okay, so we're going to talk about sequences and series today. So we're going to relate sequences, which is what we talked about last time. We had the pattern of numbers that continued on, possibly forever. And we're going to talk about how they relate to series, like a series, like as a television series. So what we're going to do is we're going to evaluate finite arithmetic and geometric series, as well as we're going to use a summation notation. So we're going to talk extensively about those two things. How do we get arithmetic and geometric series? What is a series? And what is summation notation? So those are the main focuses of this presentation today. So first we're going to start with the definition of a series. A series is what you get when you add all of the terms of a sequence. So when you have a sequence, there was commas between the numbers and the numbers were separate from each other. A series is when you take that sequence, change those commas to plus signs, and then add all the numbers in the sequence. That gives you a series. Now both sequences and series could either be infinite or finite. Now finite is the opposite of infinite. It means it has an endpoint. Something that's infinite does not. The series or sequence will go on forever and ever and ever. And what we're going to do today, we're only going to be dealing with finite series, which is going to make our lives a little bit easier. Infinite series are possibly more interesting, but really too in-depth to talk about in this time of the year with the amount of time left. So just to show you what I'm talking about, we have sequences, we have series, and we have finite, and we have infinite. So this first thing, 9, 12, 15, 18, that's a finite sequence. Okay, it's a sequence because it has commas. Those are separate terms. And it's finite because there's only 4. There's no more. It doesn't go on forever. There's just 4 terms. It's a finite sequence. Now, just because it's finite doesn't mean it has to be 4. It could be 5. It could be 6. It could be 3 billion terms. But the idea is that the list eventually comes to an end. So a finite series would be then to take those numbers in the sequence, the 9, the 12, the 15, and the 18, and instead of putting a comma between them, add them. And if you wanted to evaluate the series, then you would actually find the sum and come up with a single number, like when you add 9 plus 12 plus 15 plus 18. An infinite series is similar. It goes 3. This one, for instance, is 3, 7, 11, 15. But you'll notice it ends with those 3 dots. Those 3 dots, otherwise known as an ellipsis, mean that the sequence goes on forever and ever and ever. So it's an infinite sequence. It's still a sequence because there's no plus sign, but it's infinite because it doesn't have a fixed number of terms. Likewise, the series would be just to take that infinite sequence, but sum all of the terms. Now this means that you're going to have an infinite amount of numbers that you are trying to add. So in most cases, that means you can't find the actual value for the series because you're adding an infinite number of numbers and the numbers keep getting bigger, and you can't say the answer is infinity because infinity is technically not a number, it's a concept. So you can't say, oh, the answer is infinity. So you can't come up with an answer for many infinite series. That's not the case for all of them, but that's, again, beyond the scope of what we're doing here today. So I'm going to show you 2 formulas. I'm not going to worry about showing you how to derive these formulas or anything, or where the prompt comes from. These are the 2 formulas that you're going to use today, and this is going to accompany the 4 formulas we saw last time. The 4 formulas we saw last time were the arithmetic, recursive, and explicit formulas, as well as the geometric, recursive, and explicit formulas. So these are the 2 we're doing today. So these are series. The first one is a sum of a finite arithmetic series, and the other one is the sum of a finite geometric series. Now let's talk about what these mean. The Sn means the sum. S is for sum. Remember, the sum is the answer to an addition problem. So when we have a series, we talk about its sum because that's the answer. That's the value of all the numbers added together. So the sum of n terms, so that's what the n means, equals n over 2, where n is the number of terms, so the number of terms divided by 2, and then in parentheses you have a1, which is the value for the first term in the sequence, plus an, which is the value for the last term in the sequence. If you do that formula, it'll give you the actual sum of all the numbers in the series. It's just like a shortcut. Similarly, for geometric series, we have the sum of n terms equals a1, which is the first term, times 1 minus r to the n, and you'll remember r is the common ratio, i.e. the number that you multiply each time to get to the next number in the geometric series. N is still the number of terms, and you divide that by 1 minus r, where again r is the common ratio for that specific geometric series. Okay, so let's put those formulas to the test. Here I have two finite series. Now, in order to add them, I need to know, I could just put them all in the calculator and add them, blah, 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 blah. But I'm working on using a small series to show you an appropriate method for using a larger series. So the calculator will work and will get you the answer. I'm not saying it won't. But if this series was any larger, you could use this method. And if the series was, you know, a certain largeness, if it was big enough, you could do it quicker my way than you could with the calculator. You might even be able to do it quicker my way than with the calculator right now. I probably could, if I wasn't explaining it to you. So first we have this first sequence series, okay? And we have to determine, before we can figure out which formula to use, we have to determine if it's arithmetic or if it's geometric. So let's take a look at it for a second. And I'll see for each term I go from 21 to 18 to 15 to 12 and so forth and so on. Now every time I do that, I'm subtracting 3. So that's going to be the pattern, and that's going to be make it an arithmetic. But instead of saying minus 3, I would say it's plus negative 3. But you'll see, to get to every term, you add the same number every time, rather than multiplying the same number every time as you would if it was a geometric series. This being arithmetic, we're going to use the arithmetic formula. Okay, where S sub n equals n over 2 times a1 plus an. And in this case, I'm going to count up the number of terms. I can see there's the 21, the 18, the 15, the 12, the 9, the 6, and the 3. And altogether, that's 7 terms, right? There are 7 numbers in that series. So that's n. The n is the number of terms. So that's going to be S sub 7 equals 7 over 2. The first number in this series was 21, and the last number in this series is 3. So I put 21 plus 3. Now I just go ahead and evaluate that expression. So 7 over 2 is 3.5, and 21 plus 3 gives me 24. So now I do 24 times 3.5, and that gives me that S sub 7 is 84. So the sum of all those numbers in that series is 84. For the second one, I again have to first determine if it's geometric or arithmetic. Now if it's arithmetic, that would imply that I add the same number every time to get to the next number in the sequence. And in this case, that's not the case. Because to get from 1 to 2, I add 1, but to get from 2 to 4, I have to add 2. That means it can't be arithmetic. So let me see if it's geometric. Geometric means I multiply times the same number to get to the next number of the series. So, okay, to get from 1 to 2, I have to multiply by 2. To get from 2 to 4, I multiply by 2. To get from 4 to 8, I multiply by 2. So you can see, to get to the next number in the sequence, you're always multiplying by 2. That makes this a geometric sequence. And because it's adding, it's not a sequence, it's a series. So we'll use the geometric series formula. That's S sub n equals a1 times 1 minus r to the n power over 1 minus r. Again, r is the common ratio, which we just discussed was 2. A1 is the first term, which in this case is 1. And n is the number of terms. And this one has the 1, the 2, the 4, the 8, the 16, the 32, the 64, and the 128 for a total of 8 terms. There are 8 numbers in that row. So I plug those things in. So I have 1 times 1 minus 2 to the 8th over 1 minus 2. Okay, that becomes 1 minus 256 over negative 1, because 1 minus 2 is negative 1, and 2 to the 8th is 256. 1 minus 256 is negative 255, and negative 255 divided by negative 1 is 255. So the sum of those numbers is 255. Okay, so here we have more of the same, just to give us more practice. The first series has 5 terms, and we have to determine if it's arithmetic or geometric. So we're going to look and see if it's arithmetic first. That would mean that you add the same number every time to get to the next number. And in this case, to get to 17.3 to 19.6, you have to add 2.3. And if you add 2.3 to that, you get 21.9. And if you add 2.3 to that, you get 24.2. And so we have it working. This is an arithmetic sequence, the arithmetic series, I should say. So we use the arithmetic series formula. That's S sub n equals n over 2. We've been through this before. Now I'm going to plug in all the different things. So in this case, n is 5, because there are 5 terms. A1 is 17.3, that is the first term, and 26.5 is the last term. So 17.3 plus 26.5 will give me 43.8, and 5 over 2 gives me 2.5. Multiply those two things together, and you get 109.5. That's the sum of those 5 numbers. Now we're going to look at the next one. We're going to have to determine if it's arithmetic or geometric. It's looking pretty clear that it's not arithmetic because 7 to negative 35 means I have to add negative 41. And if I add another negative 41, I'm certainly not going to get 175. I'm not sure what I'd get, but I know it won't be positive because I'm going to keep going farther and farther negative. So this positive, negative pattern really speaks to a geometric pattern. So let's take a look and see if we can figure out what the common ratio is. So if I multiply 7 and get negative 35, I'm going to have to multiply by negative 5. If I multiply negative 5 by negative 35 by negative 5, I will get positive 175. Multiply that by negative 5, I get negative 875, and hopefully you can see what's going on here. This is a geometric pattern, and the common ratio is negative 5. So I'll use my geometric series formula. I'll plug in everything that I know, which in this case I know it's 5 terms. I know the first term is 7. I know the common ratio is negative 5, so I put the negative 5 in the 2 places where the r is, and I put the 5 where the n is. Now I go ahead and solve this out. On the bottom I have minus negative 5 changes to plus 5, and negative 5 to the 5th power is negative 3,125. That's something you're probably going to have to use a calculator to figure out, and that's okay. But now I have 1 minus negative 3,125. That is 3,126 because minus and negative is the same thing as plus a positive. So that's like 1 plus 3,125. So I do 7 times 3,126, and I divide that answer by 6. And when I do that, I get 3,647 for the sum of those numbers. So here's the kind of word problem you're going to see. You'll see this actually on the test. It's not this exact one, it's a similar one. So what I have is I have this stack of bricks, or blocks, or whatever you want to call them. And you can see on the first row I have 1, on the second row I have 2, and on the third row I have 5. And I want to know how many bricks would you use to make a stack that's 10 rows high. Now you have to be careful. What I'm not asking you is I'm not asking you how many bricks are in the 10th row. That's pretty easy to calculate. It keeps going up by 2. What I'm asking you is when you get to that 10th row and you have all the bricks on the bottom row, how many bricks did you have to have all together to construct that pattern? And what that is that's a series, right? Because when you're doing that, what you're doing is adding the number of bricks in the first row, plus the number of bricks in the second row, plus the number of bricks in the third row, all the way up to the number of bricks in the 10th row. And we just discussed this. What kind of series is this? Well, it's not going to be geometric. As you go down the row, you're not multiplying the number of bricks. To get from the first row to the third row, sure, you could multiply by 3. But to get from the second row to the third row, to get from 3 bricks to 5 bricks, that's not multiplying by 3 anymore. So this can't be a geometric sequence that we can evaluate the finite series of. What this is, though, is arithmetic. For every row, there is going to be 2 more bricks than there were in the previous row. That means to get the next row, you have to take the previous row plus 2. That's the definition of an arithmetic sequence. It's always plus 2. So let's use this series formula for an arithmetic. We decided that we want to find the 10th row. That means we want to do 10 terms. So we know S is 10, we know N is 10, we know A1 is 1, but we need to find the last term. We don't know what it is yet. We don't know how many rows are in the last row. So we're going to have to calculate that using the formula that we had last time, which is this. This is the formula for finding the nth term of a sequence. So we need to find the nth term, so we need to know what the 10th term is to find out what the sum is. This is from last time. So we plug in the 10. We know N is 10, we know A1 is 1, so we plug in 10 minus 1. The common difference, how much do you add for each row, is 2. So we just solve this out now. So we have 1 plus 9 times 2. 9 times 2 is 18. 18 plus 1 is 19. So we know that A sub 10 is 19. And we can plug that back into my sum formula to get my final answer. And that's what I'm going to do right here. So I do the parentheses first. 1 plus 19 is 20. And 10 over 2 is 5. and 5 times 20 is 100. So in order to make a row, in order to continue that pattern of bricks and make it 10 rows high, you need to have 100 bricks. Okay, let's get to the last objective here, and that's using summation notation. This is what summation notation looks like, and I don't want to scare you with it. It's not that complicated. It looks way more complicated than it really is. The first thing the summation notation has is that giant sigma. A sigma is that funny Greek-looking E thing, or a sideways M. Again, it's not an E, it's not a sideways M. It's the Greek letter sigma. It's not the Greek letter E, it's sigma. Okay, sigma is actually the Greek letter for S. So you've seen that letter before, and in this case, it's the Greek letter S, it's S for sum. Now there are three things associated with that sigma that go around it to make summation notation. The first thing is the smallest n goes on the bottom. You have to put whatever number you're using as what's called the index. For us, we'll always just use n, but that could be a p or a q or whatever. That just wouldn't the formula had to have a p or a q in it. So the smallest number that you're plugging in for n goes underneath the sigma. On top of the sigma is the biggest number you're going to be plugging in for n. And to the right of the sigma goes the explicit formula you use to find all the different n's in the sequence. Okay, it's a sequence that we understood by putting that sigma next to it, that it's a series because you're summing that sequence that you've demonstrated by the explicit formula. Okay, this will make a little more sense when I actually show you an example of how this works. So let's say we have this. We want to find that sum. It's 5n plus 1 is the explicit formula, and I want to find from n equals 1 to 3. Okay, so I've already kind of done the first part for you. The bottom part, the bottom underneath the sigma says n equals 1. That means the first number you're plugging in for n is 1. So I plug in 5 times 1 plus 1. I just replace the n with a 1. Okay, from the 1, I go up one number at a time until I get to the top number of the sigma, which in this case is 3. So after 1 comes 2. Okay, so I do 5 times 2 plus 1. After 2 is 3. That's 5 times 3 plus 1, but now I've reached the number that's on the top of the sigma, so I stop there. Okay, and what I'm going to do is add those things. And I've already got started underneath. If you do 5 times 1 plus 1, you get 6. 5 times 2 plus 1 is 11. And 5 times 3 plus 1 is 16. So now I have three numbers, and I add them. I add the 6, the 11, and the 16. 6 plus 11 plus 16 is going to give me 33, and so the evaluation for that sum, when it says evaluate this sum is 33. For extra practice, let's show two more examples. Okay, so in the first example, I have evaluate the series n minus 3 from n is 1 to 10. So what that means is I'm going to plug in 1, and then 2, and then 3, and then 4, and I'm going to sum them all together. So I have 1 minus 3, plus 2 minus 3, plus 3 minus 3, plus 4 minus 3, and I'm not going to have enough room to write everything. It's going to keep going up all the way up to get to 10. Okay, then I just calculate each one individually. So 1 minus 3 is negative 2, 2 minus 3 is negative 1, 3 minus 3 is 0, 4 minus 3 is 1, and then 5 minus 3 is going to be 2, and all the way up to 7. So you add negative 2 plus negative 1 plus 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, because that's going to be all 10 terms, and you'll get 25. Okay, the next one, the tricky part, is to look at the bottom index. This one doesn't start at 1, this one starts at 2. So you have to start at 2 as well. So we don't have 1 squared because it doesn't start at 1. We start with 2 squared, and then 3 squared, and then 4 squared, and then 5 squared, because you have to square each of them, because that's what the n says to do. So 2 squared is 4, 3 squared is 3, 4 squared is 16, and 5 squared is 25. When you add 4 plus 9 plus 16 plus 25, you get 54. So now what we want to work on is going the other way. I'm going to not evaluate the sum, because this is going to be a long one if you try to evaluate it. I just want you to write what I describe in words in summation notation. So write it in the sigma notation. So the first thing I have to do to get sigma notation is I have to have an explicit formula. So in order to get the explicit formula, I'm going to write the term number and the term in a chart, just to make it easier to look at so that I can see the pattern here. Now, what's the formula for going from n to a sub n? How do we get from 1 to 3? And do the same thing and get from 2 to 6? And do the same thing and get from 3 to 9? hopefully you can think of a pattern there, and you can find that the pattern is you multiply n times 3. So we can say that a to the n equals 3n. So that's going to be the formula that's going to go next to the sigma. So if a sigma has a 3n next to it, we just have to determine where does it start and where does it stop. Well, we already know that the first term we're plugging in is 1, because the first n we're plugging in is 1 because that's what we have in our chart. The first n is 1. And we know we're going to have 33 terms, so we go up to 33. So we put n equals 1 underneath the sigma, we put 33 on top of the sigma, and that covers our basis. Again, the formula is 3n. That's all you have to do to write it in summation notation. I did not ask you to evaluate it, so you don't have to add all the numbers from 3 to 33, or the first 33 terms of that pattern. Okay, that leaves us, that's the end, so that leaves us with the homework. It's page 148, 2 through 20 even. Good luck with that, and I will see you next class. Unless you're a senior, then I won't see you again. Okay, good luck everybody.